Good evening, ladies and gentlemen, and thank you for joining us tonight with the Mpumalanga Centre webinar on Principles of Practical Machine Learning. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Mpumalanga Centre playlist. This channel is updated regularly, so ensure you check back as often as possible for new uploads. And please click on the link that will appear in the chat box shortly to subscribe to the SAIEE TV channel. It's free. A certificate of attendance will be issued a few weeks after this webinar once we have received the CPD validation number from EXA. I'd like to introduce you now to our speaker tonight, which is Dr. Lydia Orit, who is the Product Manager, Process Monitoring at Stone 3. Lydia is a member of the Southern African Institute of Mining and Metallurgy at the South African Statistical Association. She serves on the Executive Committee of the South African Council for Automation and Control. Lydia was the co-chair of the National Organizing Committee for the 18th IFAC Symposium on Control, Optimization and Automation in Mining, Mineral and Metal Processing, held in 2019. She also serves as a reviewer for established journals like Control Engineering Practice, Minerals Engineering, Minerals, and Journal of Southern African Institute of Mining and Metallurgy. I hand you over now to Dr. Lydia Orit.
Hello, everyone. Thank you for the introduction, Minx. Very kind introduction, and thank you for the invitations by the SAIEE, and specifically Louis Kok from Sasol, who invited me to just share some of my thoughts and experiences on practical machine learning. So I've subtitled it Experiences from Academia and the Mining Industry. So up until end of 2018, I was a researcher and a lecturer at Stellenbosch University, and my field of interest was machine learning, specifically for process monitoring. And then it was fantastic to get an opportunity to see what the world is like in industry, where I joined Stone 3 as in the process monitoring team there. And it's been fascinating 2.5 years in industry now. So I think it's nice to reflect on the different realities and practicalities of machine learning from an academic perspective and from an industrial perspective. Right, so let's get going. And Minx, if you can maybe just indicate that my screen is working and you can see my agenda slide, everything's okay?
Yes, everything's perfect, thank you.
Perfect, cool. So I'm going to give a brief overview of some machine learning concept. This isn't a theoretical lecture on machine learning, but just to ground ourselves. Then I will talk a little bit about machine learning and mineral processing, specifically from my academic days, where we did a review article on machine learning and mineral processing as it was published in academic literature. And then more from my industry experience now to reflect on a structured approach for doing machine learning and data analysis that has impact, that adds business value. So those are some of the things we want to talk about tonight. So just where am I working now? I'm working at Stone 3. So it's an operational productivity and people productivity solutions provider. So you can see a cool image here of a truck tipping its ore into a crushing section. And this is showing machine learning in practice in real-time solutions where we use convolutional neural networks to detect the back of the truck and the ore and all kinds of interesting things that's of business value for that. Other than machine vision sensors in the mining industry, from an operational productivity perspective, we also provide remote monitoring and diagnostics. So that's closer to my background, process monitoring. And then another aspect that we look at is at people productivity. So those are also some machine learning solutions looking at video analytics, CCTV footage from production sites, looking to detect people in forbidden zones, PPE, COVID-19 issues like social distancing, etc., as well as other health risk assessment and telehealth kind of services. So it was coming from academia, it was quite exciting to join a company like Stone3 where machine learning and in the smart sensors was so embedded as part of the business proposition. So my talk today, when we get to more of the practical aspects and the examples, will focus on a mineral processing context. So I think it's worth just touching base about what I mean with that. So mineral processing is taking raw material from typically from open cast or underground mines and going through the transformation processes to finally deliver a valuable processed material. So this typically involves size reduction. So you want to get the material nice and small so that the valuable materials are exposed or liberated, so you can start separating them with physical separation like flotation and pyrotechnical separation like smelting and chemical separation like leaching. So this is like other metallurgical operations or chemical engineering operations. These process plants are typically operated continuously. They're very connected in terms of how everything feeds into each other. They're controlled by complex control systems, very hierarchical. So you've got regulatory and supervisory and optimization controllers all regulating the systems. There's a lot of rework and recycle. So it's quite a complex data generation activity if you think about it from a machine learning perspective. The type of data that's typically accessible in such operations, and data is of course important when we talk about machine learning, because that's the data-driven methods need data. So typical online data on mineral processing circuits are physical property sensors at the order of seconds, mass flow rates, densities, temperatures, pressures. And image data, which is in the last 30 years, 20 years, exploiting the value that one can get from image data or even laser data. So these are looking at rocks on conveyor belts and flotation froths. They can have a higher frequency than that, but let's call it minutes. Then there's offline data that's accessible in slower frequencies depending on the sites, like laboratory data on particle size distribution and metal content. More image data, for example, looking at core samples from the mine, how are things distributed before the minerals are, the ore is size reduced. And then lots of interesting text data in the form, very unstructured form sometimes more structured in the form of maintenance logs and metallurgist reports and things like that. So certainly many interesting, sometimes disparate, disconnected data sources, but that's the context of the type of data generated in mineral processing plants. Right, okay, so now that we understand, or you at least understand what kind of data we talk about when we talk about machine learning and mineral processing, let's have a look at where this fits in with machine learning. So machine learning is just in the simplest form is a simple is a modeling approach, and there's different types of models that we can learn, but it's data driven, and there's a basic structure to how machine learning works, and this learning from data is not new. I mean, we've been building regression models for more than 100 years, but there's a few things that make machine learning particularly interesting and important these days. But let's get some basic definitions. So we've got, for most machine learning types, we've got some output Y that we want to learn from some inputs X through some functional form F, and this functional form is defined by a set of parameters theta. So these output variables can be continuous. So this might be trying to predict the final mineral content in the product of a mineral processing plant, or it might be categorical. So it might be a class label. You want to predict if something is normal or abnormal, or whether something with a specific type of mineral content. So in terms of the input variables, these can be continuous or they can be categorical. So you can have temperature measurements, or you can have reagent types, which is an example of a categorical variable. So then the next thing to consider in this functional form is the parameters. And it's quite important in machine learning to differentiate between model parameters and hyperparameters. So model parameters are the parameters that learned during the training of a machine learning algorithm. So for example, if we think on a very simple linear regression model, y is equal to mx plus c, that would be m and that would be c, and the values of m and c would be fixed when you estimate them from a historical data set. Hyperparameters are design choices. And machine learning algorithms are typically have got very interesting structures, and they've got very interesting design decisions to make. And these are all tuned according to their hyperparameters. So example from regression would be if you did a polynomial regression, so first, second, third order terms in X, and you the model parameters would be your beta zeros, beta 1, beta 1, 1, beta 1, 2, etc. But your hyperparameter would be closer to the design choice. What order of polynomial model am I going to use? And that will, as soon as you choose your model order, the hyperparameter, your model parameters will then become fixed in what they are that you need to estimate, and then the training data will help you set those values. Now, these hyperparameters are important in machine learning because they also need to be estimated, or they need to be specified by the user. So you have to have a good approach of how to select these hyperparameters, or how to at least make sure that you're not selecting suboptimal hyperparameters. So F is interesting, and there's a whole zoo of different types of functional forms that is available now, easily accessible, whoever you are, open access, lots of different types of machine learning models that you now have access to. And they can be parametric or non-parametric. So for example, very clearly defined model structures, the parameter driven like linear regression, or non-parametric, where such as neural networks, where there's still parameters, but they're just hidden in layers of abstraction. So how do we know what, or how do we get the best functional form so that we can predict Y accurately from X? We've got two phases of training. We've got, or two phases to accomplish that. we normally have a training phase, and that's where we learn the model parameters. And we typically want to minimize some objective function so that we can learn the best model parameters. For example, sum of squared errors is a typical objective function. But we, for machine learning, because we've got these hyperparameters that can have such a big effect on the functional form and can have such a big effect on the final learning, we need to have an extra phase in our construction of F to make sure that we get the best structure of our machine learning models that we possibly can. And that's typically called the validation phase. And that's where we learn the hyperparameters. So we don't want to just, for example, test one model, polynomial model order. We want to test a couple to see which is best. So that's in a nutshell kind of the thinking around machine learning functional forms and their inputs and outputs and those parameters that's so important. Now, there's a couple of different flavors of machine learning. It's not just as simple as y is equal to fx theta. It gets a little bit more complex than that, and I'll just mention these types so that you're awareness of it, and we'll talk about some of these types a bit later. One of the types is supervised learning, and that's kind of the workhorse, and it's the most easily kind of understood and probably the most techniques around that. So supervised learning is exactly that functional form. Y is equal to fx as a function of theta. And one can further subdivide supervised learning depending on whether you're trying to predict something that's continuous, which we call regression. So you can just see this x1 and x2, the inputs y, the outputs. We're trying to estimate this model surface. If y is categorical, for example, here we've got yellow dots and blue dots. The task of predicting whether something belongs to the yellow class or the blue class, that is supervised learning, but it's called classification. Interesting field of subdivision of machine learning is unsupervised learning. So supervised learning means it's supervised. You have correct examples. You've got historical data of, you have examples of X that correspond to the specific outputs of Y, and you want to match them. Unsupervised learning is exactly that. It's unsupervised. There's no labels. There's no correct answers. In fact, there's just no Y. There's no output variable that you're trying to predict. But there's a lot of interesting concepts from supervised learning that one can adapt so that it can become unsupervised learning, or even just develop machine learning methods from scratch. So why would we want to do unsupervised learning, or what kind of supervised learning is there? The first type is for noise removal. And the little picture that I draw here is where we have three-dimensional data that might not actually have as much, might have some noise. And by estimating how that three-dimensional data could be represented on a two-dimensional surface, and removing the variation in the third new dimension, you can simplify and clean the original data. So the formulation there, x hat, or a noise-free approximation of x, is a function of the original x data and then the model parameters and the hyperparameters. So that is denoising. You want to remove noisiness from your input data. That you can then do supervised learning on, for example. Another application of unsupervised learning is for feature extraction. And this is to say that your original data X has perhaps a lot of structure in it, but it's very high dimensional, and it's difficult to find the structure, the constraints, the lower dimensional manifold that it is constrained to by just looking at using bivariate or data visualization techniques. So what feature extraction aims to do is try to find new definitions of variable combinations in your original input space so that these features, these new vector directions, these new components in your original space better capture and explain the variance that's in your data. So that is this equation down here. T is equal to fx of theta, where T is now a transformation of x. We don't have labeled data for T at all. It's a new feature. It's a new variable set that we've created, but there's some properties of T that's desirable that we want to use. For example, if we look at T, we can see more interesting correlations, or we can use T as input to supervised learning. So that's an interesting application of unsupervised learning. Another type of unsupervised learning is clustering. And with clustering, we have a sense or a suspicion, or we're exploring our data where we think there might be distinct categories in our data, but we don't have labels for them. But we feel from our domain knowledge that there is different generating processes in our data set. And we want to find in an exploratory step, we want to find those partitions between clusters in the data. So in the equation formulation here, we're just given X, and we want to learn C, where C indicates some cluster membership. But we don't have historical examples of it. We don't know previous cluster membership, but we would rather want the machine learning algorithm to discover clusters from the data, given some good definition of how what constitutes a viable cluster. So the little picture here shows that this data set, if you can imagine what it would have looked like without the colors, if a clustering algorithm is applied to it, the data can be separated into points that are more similar to each other than to other data points, and those groups are clusters, and they can then be further used just for interpretation and exploration purposes. Why do these samples cluster together? Is there something that we can learn about the data generation and the processes underlying that? Now, supervised and unsupervised learning is probably the most represented and the most popular of machine learning techniques. Unsupervised learning dramatically less so. It's still there, but not so prevalent, I would say. And then semi-supervised learning is also one of those fringe things, but it's actually quite useful. And then reinforcement learning is very interesting, very popular. That's what drives things like AlphaGo. But it's a form of machine learning, but it's quite a distinct form of machine learning. Semi-supervised learning is a form of supervised learning where you still do regression and classification. But the interesting thing about semi-supervised learning is you've only got a small labeled set where for all of your cases of X, or all of your rows in your matrix of X, you've only got some of them that has got labels where you know, okay, for this manifestation of X, this is what my output label was. But you have a large unlabeled set. So you have observed a lot of extra information that you don't want to just throw away. You just don't want to just discard. So what semi-supervised learning does is it makes some assumptions about your data to help you exploit the unlabeled X to make a stronger model. And those assumptions are typically in terms of continuity or clustering in your data. And there's this little picture here on the left-hand side with the white dot and the black dot. Those are the only labeled examples, and if you only use them, it would be a very small data set to build a model on, but your decision boundary would have been as indicated. However, if you had a lot of unlabeled examples, given here by the gray dots, the assumption of continuity and clustering might help you make a much more complex separation boundary. So that's quite an interesting field of machine learning as well. Reinforcement learning is kind of like its own paradigm, where you've got an agent, so some decision-making entity that's coded that can, on its own, take an action in an environment. And that action, in terms of our data sets, we can think of that as a subset of the input variables in our data set. And this, the results of this action can be observed in terms of the state of that agent in its environment. And the state of the environment are both captured in terms of its inputs and its output variables. And then, depending on the state, there's some reward that this agent gets. So it moves closer to some goal that it wants to achieve. And that might be related to one of those output variables. So reinforcement learning is quite interesting. It's this alternating approach between being able to find good data. So it's different to the other techniques because it actually has agency to collect more data and then use the collected data to learn better about the environment so that it can take an action again. So the big difference between reinforcement learning and the other types of learnings is the fact that you are continually updating your data set in order to achieve your goal, and you let the agent loose, they can do it themselves. So those are some of the basic definitions of machine learning. Now, given these types of machine learning approaches, there's a plethora of machine learning techniques that's just exploded in the last 20 years, 30 years. A lot of these things have been around a long time, but just due to more data and more accessible computation, they've come to the fore. A couple of algorithms are quite new and quite exciting, and it's quite accessible these days for anybody to play with it with a little bit of coding experience. So it can be quite overwhelming. But there's lots of interesting kind of cheat sheets and recommendations from different coding platforms to aim to help you select the appropriate techniques to use. For example, a popular package in Python to do machine learning is scikit-learn, and they've got this nice little cheat sheet to help you figure out what kind of problem am I dealing with, and what, as a first glance, thumb rules, what is a good technique to use for that purpose. And just to show that, other environments like Microsoft Azure has also got these similar machine learning algorithm cheat sheets. So we really are spoiled for choice and spoiled for accessibility in terms of being able to select and apply machine learning methods. So I'm going to just that's kind of the section of the talk that was machine learning basics. I'm going to start talking about a few details of specific methods that will later touch on some of the applications, but also just to get into a little bit more of the meat of some of these things, especially as they apply to mineral processing. So the for unsupervised learning, there's interesting application for the noise removal or the feature extraction is for anomaly detection. So anomaly detection is there something that happened in my process that is very different to how my process normally behaves. So I've got good normal operating conditions. Everything is as they're supposed to be. Variables are interacting with each other as they're supposed to be. And then every now and then some anomaly occurs. And this might be to a failure of an instrument, or to a failure in a process unit, or due to an operator suddenly changing a set point that's never been done in that way, or it can be an disturbance from upstream or something like that. So the way that the kind of the grounding for how to think about unsupervised learning for that application comes from a workhorse from statistics called principal component analysis. And it's probably an interesting question whether principal component analysis itself machine learning. It's been around for probably nearly 100 years, so it's quite old. And it's a statistical technique. Whether you want to call it machine learning or not is probably not too important. Okay, it's a linear approach. So linearity is good because it makes a little bit more conceptual sense, but it's bad when it comes to structures that are not linear, where they might not fit as well. So this is unsupervised. So we don't have an output that we're trying to predict, but we're trying to capture the variation that there is in our data in a sensible way so that we can interrogate that variation. So this little picture that I show here is just to show that if we have a three-dimensional space and we can see our data's got a very specific structure, the output of principal component analysis would give us a new rotated and scaled a system of features related to each other. For example, instead of representing our data by x1, x2, and x3, we now have a new a reference system, T1 and T2, and there's a T3 sitting in there as well, that better reflects where the variation in the data is. Now, how PCA is used for anomaly detection is if we look at this new plane of our data, T1 and T2, we've got some dimensionality reduction. We no longer have 3 variables to look at. We've only got 2. So how we can do anomaly detection with unsupervised learning is in 2 ways. We can look at how far our process data deviates from that plane of expected variation. And if it's deviating from that plane too much, it says that something new has happened. There was normally not a lot of variation from that specific plane, but now there is. So something has changed. There's been a change in the correlation between the variables. So there must have been a change in the process generating those variables. Another way to look at anomaly detection in this reduced space is to look at along the plane. So assuming that my noise removal is still valid, am I further from the origin of this plane than I've been before? Then it means I'm just in an extremum. But that the reason to look across the plane and not at x2, x1, x3 in isolation is because that plane distance takes into account the variation between variables. So that's just a grounding on, how unsupervised learning can be used for something practical, for example, anomaly detection. Now, where does machine learning, well, more recent or more commonly understood machine learning techniques fit into that? There's one example of that involves neural networks, and it's something called an auto-associative neural network, and it's a nonlinear approach. That there's some benefits there if your underlying distributions are nonlinear. And the auto-associative comes from the idea that your original data is the inputs to your neural network, and the outputs that your neural network is trying to predict is the original data. So you're putting X in and you're trying to predict X out again. However, how you learn something interesting from taking X and trying to predict X is you introduce a bottleneck. You force your model to try and capture your original input data in fewer dimensions. So for example, in this neural network down here, we've got our input layer that's taking in all of our input variables, and then we've got a connected hidden layer. Neural networks just do nonlinear transformations and summing from each of its nodes to the next. And then it forces, there's a layer where all of the information and all of the variation in our original X data is squeezed through this S1 and S2 data. So we do feature extraction and here where everything that we are retaining about the information content in our data must be represented in only 2 dimensions. How would we have known what these 2 dimensions, whether we picked good ones? Well, that's where we needed an output that we tried to model. So the best way to know if S1 and S2 captures the information in X is just to try and predict X again. So if we can take X, squeeze it through S, and still get a good representation of X out of it at the end, then that is a good noise removed feature extractor. So we can think of this S as the principal component for this neural network, and it's called auto-associative. Auto just means self, so X is trying to learn itself by association with some features. So there's some pretty pictures here where it kind of illustrates what is possible with these techniques. So just as PCA gave us this 2-dimensional manifold whereupon our data can be projected, an auto-associative neural network can also give us a manifold, so a reduced dimension surface, but it's non-linear. It can fold. It can tear, in fact, but it can fold. So here is just 2 examples of an auto-associative neural network called nonlinear PCA that is trying to fit the shape of this very interesting and tricky cylindrical data, which is just an academic example. I haven't seen that in process data before. And then if we would now flatten out this nonlinear manifold and project the data onto it so that we can measure distance from the manifold or measure distance along the manifold for anomaly detection, this is what it would look like. Just for interest's sake, machine learning and neural networks are really cool and accessible and a hot topic these days, but something like this auto-associative neural network has been around in its application form in chemical engineering since 1990. A guy called Kramer did it. But in the 90s, there just wasn't enough data and there wasn't enough computational resources to make these techniques successful. Sorry. Right, so there's some method in the madness. The auto-associative structure and these unsupervised learning model are quite link quite nicely to kind of the cutting edge supervised learning techniques that's used for machine vision typically. So for example, convolutional neural networks are a type of neural networks as well. Sorry, I'm just gonna. Where you also have connected layers the convolutional networks are quite special in the way that they've got a very special connection between the nodes and a filter that moves across the image. But nevertheless, there's also a similar structure in terms of bottlenecking. UNet is a popular one, but the importance is it's a supervised technique, so it needs a lot of hand-labeled images. Apologies, my COVID hasn't quite left me. Okay, cool. Let's go on. Right, so that's showing you some little bit more detailed example of some of these techniques. And now I will just show you a little bit about how what are the kinds of applications that machine learning methods have found specifically in mineral processing. And I worked with a colleague at Stellenbosch University in 2018 to publish a paper on where we did a review to have a look at these techniques and to see where are we on this hype versus reality, maturity, visibility, Gartner hype cycle. Because there's a lot of hype for machine learning methods. So it would be quite important to understand, you know, where are we and is it overhyped, and what are we seeing, at least from academia. And one of the main things to understand when it comes to why is there so much hype at the moment is just because we're in an amazing position currently in terms of just the amount of data that we collect, and having that raw material to really learn from the data. And I mean, Facebook and Google and Apple and all of these companies have some really headline grabbing applications and performances with machine learning models. But it's a good sanity check for your own application to just understand we're talking about millions of records for completely defining a specific application, whereas maybe in process industries we're not, even though we might have millions of records, if we look over a couple of years, is it fully observed? Nevertheless, still a lot more data, so that really does give potential to machine learning methods. Another reason for this hype and then potential value add is just better computing. And it's not only about computing in the sense that computers are better and more CPU power, more GPU power, more storage, etc., etc. It's also about the idea that we now have computing as a service. So you don't have to buy a supercomputer for your company or for your university department or even for yourself. You can subscribe to Microsoft Azure or AWS from Amazon and just need the amount of computation, pay for the amount of computation when you need it and how you need it, and not invest in capital for that. So that's really been quite a pivot point in what machine learning can do. It's taken away that hurdle of computation. Another aspect is also the better methods. So there is a lot of good and interesting work that's being done on all kinds of interesting and new and sexy machine learning technologies or algorithms. And also, I think maybe more on the computing side than the method side, but it's been so democratized by open source coding languages like Python and other languages, where the open source community has just contributed so many packages that anybody can use quite easily. Okay, so our review was focused on academic publications, and that comes with some interesting caveats to just remember. But we clearly saw that there was quite a steady growth in the number of techniques that were mentioned in literature, or technique applications that were mentioned in literature. So one article could have more than one technique in it as they compare different techniques. And I think that's even taking up exponentially, just judging by the number of review requests that I get on ML and MP. Something interesting is that we did some analysis on, is to see what they're being implemented on, and I think there's just says something about academia and the fact that most of it's on experimental data, which is maybe not a good fit for machine learning methods, because experimental data can't generate the thousands and the millions of records and hundreds of thousands of records. But a barrier there is just getting access to industrial data, especially in mineral processing, where a lot of the mineral processing data is sensitive, and mining companies might not be so keen to just publish their data for anybody to use. But I mean, that does mean that there's a barrier. There's a barrier of doing real practical benefit adding machine learning research in academia. Very interesting, this authors commenting on how successful their machine learning was. I don't know if this is selection bias, only successful things get published, or maybe just some optimism on the side of the authors. And then very interesting, we also looked at the different categories, and machine vision is definitely one of the most popular applications. So this is for those three different types of applications in machine learning. We just kind of gave a one-page summary of what we observed from those articles that we reviewed. So with the one category of application is kind of a soft sensors or data-based modeling, where the idea is it's supervised learning. You've got fast and easily accessible measurements, process measurements, that you want to do predictions in real time of slow and difficult measurements for composition or things like that. And typical techniques used for that, I won't explain them all, but I mean, if it says PCA, that's not a supervised method, but it was used as part of the pre-processing, for example. So we've got neural networks and support vector machines and all kinds of interesting things. So the trends there was definitely that the database modeling mostly used for soft sensors, and the industrial implementation is, from an academic perspective, at least, relatively mature. I must say, from an industry perspective, I think there's still a lot of potential to get more out of it, or more application. Some of the challenges mentioned that we saw in these papers that they mentioned is that the data is non-stationary. So the process keeps moving to places where it hasn't been before. So your models become uncalibrated quickly. There's also multiple modes where you can switch between different recipe types, for example, and lots of other challenges, and lots of interesting opportunities there. So if you're in academia and wondering what to look at, I mean, looking at deep neural networks, adaptive retraining, when you see that your soft sensor is becoming uncalibrated, to automatically trigger the retraining of it, and taking into account dynamic behavior, for example. The next category of the three that we looked at, that was mentioned in machine learning applications in mineral processing, was for fault detection and diagnosis. So this is that anomaly detection that I mentioned, process monitoring. So the idea there is, as input, you get process measurements that's available in your historians and databases, and what you want to predict is any new sample, is it normal or is it faulty? And if you can do that, you can interrogate it further, perhaps into a fault diagnosis. Okay, if it's faulty, why is it faulty, and what can I now do to fix my operation? And there's lots of interesting, also unsupervised learning approaches to that. PCA is quite the workhorse in these applications, and then many of the techniques is just nonlinear versions of PCA. The interesting thing there is it's not really found its way into industrial application. There might be some industrial data sets that it's demonstrated on, but no continuously running applications. Yeah, so that's quite interesting. Maybe if it's an industrial publication, it's just not, industries might be doing this kind of work, but they're not necessarily publishing on it. Some of the challenges is data scarcity, more on the side of having labeled examples of whether something truly was a fault historically. It is called unsupervised learning, but you still need to assess whether it was successful or not. So having some indications of whether it was abnormal or not would be good. And then as I said, it hasn't quite penetrated to implementation, at least in how academia reports on it. Another challenge is to motivate why fault detection is worth it at all. It's easier to motivate soft sensors and why they add business value. It's a lot more difficult for fault detection. But there's definitely opportunities there, especially in not just in doing root cause analysis, and not just giving a list of original variables associated with the fault, but actually figuring out what caused the fault and how to fix it. And incorporating more diverse data like maintenance logs and technical diaries and other textual data, for example, as well. Another big opportunity is prognosis. You don't only want to know something is wrong, you want to know how long will it take before there's a dramatic failure. But that needs a lot of additional context as well. Okay. Then the third category and the most well represented in academia is the machine vision category. So there's a lot of industrial implementation out there, mostly for the simpler technique, kind of the traditional image processing techniques. A lot of the kind of more newer, sexier, interesting CNN models, and those, at least in 2018, were still just demonstrated kind of on industrial data, but not implemented in industrial data. When I joined Stein 3, I could see, well, there's actually a lot of really cool stuff that's done in industry, but maybe not just published, because there I saw convolutional neural networks actually applied in a production environment. So that's pretty cool. Yeah, I think one of the challenges, at least from an academic perspective, or is to have enough labeled images, but there's interesting opportunities there in terms of crowdsourced labeling, kind of mechanical Turks paying people a couple of cents to label images. And of course, deep nets is making a hell of a difference there. Cool. So that's a little bit on the review on machine learning applications in mineral processing, and what we saw from an academic perspective. Now I can reflect a little bit of my last 2.5 years in industry, and how that's kind of enriched my thinking of machine learning and mineral processing. I love this diagram by Iserman from 1993 on fault diagnosis on an industrial plant, because it's got little men running around when there's an alarm. But why I like it as well is it shows you kind of the complexity and reality for the environment where you want to do fault detection, and just to remind yourself that it's not just good enough for a model to predict something or flag something and throw it over the partition. There's a lot of context that needs to be understood. For example, a process is controlled and it's subject to faults. and this system generates measurements that can be evaluated to generate alarms that people have to react to, or there could be higher level feature extraction, change detection, fault diagnosis, etc., that in the end of the day needs to go to an operator that needs to make a decision on what changes he needs to do to the operation. Maybe one day or some of that decision can be fully automated, but that is quite a fun challenge if you realize what the true implication of that is, just in terms of what the machine learning should have access to in terms of data and agency. So for example, the little bit of experience I've got now in industry was mostly along these machine vision smart sensors, as well as remote process monitoring, fault detection and isolation. And something that I've noticed is the focus difference in academia and industry, and that's fine. Academia and industry should have different focus, but I think there is an opportunity to get a little bit closer to each other. And I've kind of highlighted it here, where the purple kind of shows the academic focus, and the orange shows the industry focus. So, and just for the case of, for example, anomaly detection. So a lot of focus on the process modeling and control modeling, and then also on the basics of taking the measurements and extracting features and detecting changes, maybe going a little bit more into trying to get to faults, but it's saying that there's an issue in variable x1, x5, and x17 is not enough information for the operator to take to make a change. And I think there's in fault detection research, there's maybe a little bit of being stuck in a local optima at the moment, because there's a benchmark data set called the Tennessee Eastman process, where everybody publishes on it, and it's really cool, and it's nice to have a benchmark, but the performance metric is just to detect that something's wrong, and sometimes to show which variables are involved. And that's great, but the true difference that fault detection makes in industry is if you go further along the value chain and actually understand what is the advice you have to give the human operator that he has to change in the operation to get back to normal condition. So there's a little bit of a stuck in a local optima, perhaps, in fault detection research, in terms of this is the criteria that everybody uses it, so that's what we're going to use. But to be fair, the type of data sets that's available to academia does not include all of this complexity and additional context and data necessarily. So in order to move out of that local optima of focus, it probably needs a little bit more collaboration on sharing data sets or creating simulators where these types of additional functionality is included. Okay. So that's kind of the part of the talk on machine learning applications and mineral processing, and the review that we did. Now, the last part of my presentation is to see how we can make, or what I've learned in my brief time in industry so long, in terms of making sure that when we do machine learning projects, that they're set up to be successful, and they're set up to really add value to the business. Because I think there's some scary statistics, like 80% of data analysis projects in industry fail because they didn't quite have the right focus, or they didn't quite determine whether they're worth it from the start. So I'm just going to reflect on a little bit of that in the last part of the webinar tonight. So I found a really a useful framework when just as I was leaving academia and starting working in industry, called the Cross Industry Process for Data Mining, CRISP-DM. and it's quite nice. It's a very structured approach, and if you don't just take it at face value, but really spend some time to understand the different steps, it's very useful sanity check for, am I just rushing to get some data and apply a sexy machine learning technique on it? Am I really professional and self-critical enough to make sure that I'm trying to solve the right problem? So the CRISP-M framework is very problem user client focused rather than technique focused. So that just helps keep the focus right. And it's also iterative, and it's also got stage gates, go, no go gates. So it's a good, I think, sanity check when you're doing projects like this. So the website's down there. I really recommend having a look at it. And I'll use this framework with examples in the next little while. So if we just unpack it a little bit, so the purpose of the first step, business understanding, is just to really assess the context of this application, this problem area that you've chosen to embark on, and where you see an opportunity for maybe a machine learning application, and to really just set your objectives. I think data exploration can fill available time, and it's fun and it's nice and the pictures are pretty, but there's a place for that, but most projects are not like that. So you really want to make sure that you're aiming to solve a specific problem, and also define the success criteria up front. Otherwise, you might drift a little bit during the project. Then you really want to understand your data. Your machine learning model is only as strong as your data. So you can spend a lot of, you cannot spend enough time understanding your data. And this is really, describing the data, doing a little bit of data exploration in the direction of your objectives, and of course to verify the quality. And that's where you need to spend more time talking to people involved with the generation of the data, rather than just plotting your own plots, because a guy on site can quickly tell you, oh, that densitometer, no, we don't trust that, it's always out. And you could have spent weeks trying to find interesting pictures of using your densitometer values that you had. Then there's data preparation, and this always takes a lot more time than you think if you're new to the field. So selecting the appropriate data, cleaning the data, constructing attributes is a very important step, and that's something we'll get to later. But constructing attributes basically means infusing your domain-specific knowledge of the problem into your data. Help out your machine learning models, create new variables that captures your understanding of the process. If there's some kind of energy transfer or energy transformation in your system, take your temperature measurements, multiply them by your mass measurements for the same stream, and you've got an approximation of enthalpy that your neural network doesn't have to figure out on its own. And then for the modeling technique, this is where you actually do a little bit of modeling finally, but at least by the time you get to this, you're doing it on the right data for the right reasons. Then when you evaluate your model, it's not just on your R-squared or your false alarm rate. You do that as part of your modeling test, but it's really about your model might be beautifully accurate, but it might still not exactly solve the problem that you set out to solve. So this is a step to reflect on that. And then deployment is quite interesting. What now? You've built a nice model, it works, but what does that look like in the field? And that's quite some interesting things that I've learned in the last couple of years. And I think there's definitely an opportunity to be more aware of what goes into the construction of and modeling and monitoring and maintenance of machine learning models, because it might inspire us in terms of making sure we've got the right data and selecting the right techniques, so that we know that we're set up for long-term success. Right. So in terms of this first step of business understanding, I'm going to use a little example just to show that as soon as you can, you want to start building a business case, because the types of questions that you have to ask yourself about cost benefit of a machine learning solution will really guide you in terms of making sure that you're focusing on the right model structures, and you're focusing on the right outcomes, and that what you're trying to predict, or how that prediction is going to be integrated into a decision support system or a control system, that drives the decisions that you make in terms of your modeling. So, for example, for that machine vision sensor, the pain point on site is that there's oversize coming from the mine that can damage equipment and cause downtime, and also cause large maintenance costs. So you can just say, oh, if you can just estimate what's on the back of the truck, that's enough. That's your business understanding. But it's not enough. You have to think a little bit broader and a bit deeper. But how will it work, and who will use it, and how will they use it to really help you make your machine learning problem solving practical. So, for example, the end result of this machine vision model can be that you integrate it into your automation and control system on site to such an extent, for example, that if an oversized rock is detected, you have an automatic trip of a feeder, so that the belts stop, the materials aren't processed any further, but you provide the operator with the visuals so that they can see from the control room, is this a true oversize or not? And if it's a true oversize, they can get a picker and remove the rock. If it's not, they can see it visually, they can just restart the belt. So that's thinking in our little Iserman picture, that's thinking all the way back to the actions that the operator have to make. And now, in terms of building the business case, so we have a look at, the cost benefit of the different ways in which this scenario can play out. So this is what this little graph shows on the right hand side. We have normal operating conditions, and then we have some data analytics tool, and there's kind of three paths we can take. If we have normal operating conditions and the data analytics tool makes a fault and gives a false positive, there will be an incorrect shutdown, which has some maintenance and lost production costs before we can start up again. If the data analytics tool and operator is active and the fault occurs and we've got a true positive diagnosis, that will still result in a shutdown with an associated maintenance and lost production cost, but it will be an appropriate maintenance and lost production cost. And if there's a fault and the tool doesn't pick it up, it might escalate to a failure, which might escalate to unscheduled shutdown, which is also associated with maintenance and lost production. So just playing through these scenarios of what can happen really embeds in you the impact of what can go wrong if your data analytics tool doesn't work right, and what kind of metrics do you need to focus on, because that false positive diagnosis and this missed diagnosis might have quite a big impact. So that might have an effect on what you want to focus on in terms of your accuracy and specificity indices. So in terms of how to do that business case assessment, you can look at all of these elements like number of faults and production costs and opportunities and all of this, and start to also figure out where are you going to get the data or the knowledge in order to calculate this, because that will also help you figure out when you go through your CRISP-DM framework, just making sure at the end of the day, I want to prove business value by keeping track of these elements. So let me make sure that's part of my data understanding, preparation, etc. Okay. Another important part, as I mentioned, is the data understanding part, and just some observations I want to make there is to really, as much as possible, embed your domain knowledge, your process understanding into your data analysis. Before you even see your data set, you want to draw a little system diagram and see what are my inputs and manipulated variables, what are my disturbances, what are my state variables, and what are my outputs, so that you can get a sense of what is my system, how does it work, what do I know about it, what do I know about the fundamentals, and you can kind of have a checklist of your expectations of what kind of variables need to be present and how you're going to use them, because you want your outputs of your system in terms of control theory to also be the outputs of your supervised learning algorithm, for example. Or if you're doing fault detection and want to know how can I restore my process to normal conditions, you want to focus on your manipulated variables or the inputs, the things that your operators has got levers on in the context of disturbances. So that's something that makes your machine learning a little bit more practical and interpretable. So, for example, I won't spend too much time on this, but just to show that even, for a flotation circuit, this is what a system diagram could look like. What your inputs are and what your disturbances are, what your outputs are and what your states are. And even before you've opened your data set, you've got a sanity check just to understand, are these things present? Do I need to go back and collect more data? Do I understand how these things, what I want to focus on when I build my model, or at least how I need to group my variables if I need to? And when you've got your system diagram, you can kind of already kind of understand what your model can add to your ultimate end. So if you find correlations, if you find strong models between different subsets of data, what is the implication for example, for root cause analysis? So I won't go into too much detail here, but just showing that if we find significant predictive models between just the disturbances and the output variables, that might help us with root cause identification, but it might not help us with actually figuring out what the right action is to do, because we need to find the correlation between the handles on the process on the outputs before we can directly suggest an action. And if we only find a correlation between states and outputs, that's only a proxy for the target, and it's not a root cause, because it's maybe not related to the disturbance, or there's a lot more interpretation needed. But it can just help us, focus on the problem and not just on the nice plots and the cool models that's easy and comfortable to play with, as comparison to the open-ended, tricky process understanding types of questions. Another or the next step in the CRISP-DM, and just a brief comment I want to make, this is not exhaustive, this is just some things that I've experienced and learned applying this framework, is feature engineering, or making those attributes. So the idea of creating new variables from existing input variables so that they can do a couple of things for you. One of them is to embed your domain knowledge into your data set, so that you bring that understanding into your data set. And if you create more features, that's more likely to be related to the structure of the data generating process, that makes it simpler or easier for your model to fit to, potentially, which might result in more accurate models, because instead of your neural network that also needs to figure out that you need to multiply temperature by mass at some point, if you already provided with that new feature, it can perhaps get to the result quicker with less hyperparameter tuning. The other important thing about having these engineered features is when you now try to understand your model or interpret your model, you now have easier to understand variable importances. If your model highlights that these and these and these variables are important, and they're one of these created features that's, for example, related to enthalpy, that helps you better understand your model from a domain knowledge perspective. And here I just mentioned it can be all kinds of things. I mean, you've got something called interaction variables. That's basically just a calculation. Or you've got even things like indicator variables, where you have a categorical variable which indicates some process history that you want to capture. For example, by interviewing the guys on site, they can say, oh yeah, we change the liners in our mills every now and then, and we had a period of a rubber liner and a steel liner, and you know it's got an effect on the mill load, because the mill load sensor doesn't actually measure what's in the mill, it measures the mill weight and what's in the mill. So, and that's why you have to understand where your data is coming from as well. So you have to correct for the type of mill liner in it if you want to have a consistent understanding of what's the true effect of your mill load is, for example. And you could create an indicator variable to say, well, I don't know if reagent type or if a mill liner is going to have an effect, but I'll create a new variable to say, you know, value of 0 before replacement and value of 1 after replacement. So you at least add that context to your model that your machine learning model has to learn. Cool. So in terms of modeling, you can see there's a lot of plumbing to do before you get to the actual modeling. But I think that's the more effort and you put into that, it ensures that you focus on the right type of models for the right purpose, and you don't have to iterate too much back, because you've set yourself up for success. So just adding a little bit more detail to one of those examples we saw earlier. For example, in this truck oversize detection, there's this complex model with hundreds of thousands of hand-labeled images. I think it's up to millions by now, where there's actually a couple of different models doing different things. For example, there's a CNN that's detecting in this image of the entire scene what is the back of the truck. And then there's another model that's just looking at what are just the small particles. And then there's another model looking for the particle centers. And then there's another model just looking for the particle regions. And that, in the end, the output looks like a mask identifying these different elements. So that's just to show you that sometimes we talk about modeling, but it might be a whole little community of models that's working together. Then in terms of modeling as well, just always sanity check the model assessment. Remember, we need the training data set to fit the model parameters. We need a validation data set to choose the best hyperparameters. And then we need a test data set that's completely unseen, that you're not cheating on and data snooping, a completely unseen test data to give you a sense of how well will this do in the field. How well would it do if I collected data tomorrow and just released my model on it? So if model complexity can be expressed in terms of number of parameters, or order of the polynomial or the functional structure, but the principle is the same. If the model is not complex enough, we might underfit, and if the model is too complex, we might overfit, and we can't see that in the training data necessarily. We need some unseen validation data in order to see that, and then get the Goldilocks effect of where we can choose just the right complexity of model for our purpose. This is a I think the most well-known idea of model complexity assessment, because it's easy to evaluate in isolation. But another aspect to remember in terms of model complexity is just whether the the complexity is worth it in terms of interpretability, maintainability, robustness, computational expense, and generalizability. And that doesn't come out in this plot. Um, I've seen it in some academic papers, and I probably wrote academic papers like that myself a couple of years ago, where you compare it to maybe a simple linear regression model, and you see the neural networks do better, but they do better by 1% accuracy. So that's what I mean with, is it worth it? You know, is that extra accuracy, even though it's statistically significantly different, um, for just in the light of accuracy, but is it worth it in the broader scheme of things, in terms of those qualitative factors there, which again, you have to think about your entire pipeline and how that model is going to be deployed. But just to be kind of objective and self-critical and professional, always just throw the simple model into your framework. You want to build a convolutional neural network, that's great, but just to keep yourself honest, just to keep yourself sane, put in a linear regression model, put in a linear discriminant analysis model, just put in a simple model, just to make sure that the gains you get for the complexity is really worth it. Okay. Something else I just want to mention around modeling, and I'm not going to go into too much detail, so take a note of that reference down there. It's a really good review article, but it's the concept of when we're doing modeling of complex systems, to not completely discard the fact that there's a lot of first principles and a lot of domain knowledge and a lot of fundamental models out there that we want to exploit as well. So the idea of hybrid modeling is to integrate these fundamental models with data-driven modeling. So, for example, in this a parallel structure where we can use both models to predict some outcome, and then what the benefits of the machine learning model is, it makes use of all available data and can maybe learn some aspects that were assumed away in the fundamental or mechanistic model, but the mechanistic model provides us a good starting base and is more interpretable. So really have a think about that, and read up a bit more and consider hybrid modeling for your next project. Okay, just keeping an eye on the time. So when we get to the evaluation phase, like I mentioned before, this is not an R-squared value or a false positive rate or something like this. This really takes us back to the business understanding. Are we solving the problem that will make a difference in the business, the industrial application that we're targeting? And some things that I've seen and that I've felt and have been bad at, and maybe getting better at in the last couple of years, is just to not just look at the technical performance of the model, but also to try and define during the business understanding phase success criteria. And success criteria that can measure success early on in the project and often during the project. So things, for example, just like, and that you constantly interact with your end user or your client with it often. You know, simple things like, is the data or the predictions accessible? Can people already interact with it? And then, is it useful? Is there something that comes out of this output that is useful? And then to start and see impact. do you have localized impact in just the section? For example, just in the crushing section, are we starting to see that impact? And then expanding that and to see, is that trickling up and accumulating into plant-wide impact? And then success criteria, it might be for the client, but it might be for you as well as a machine learning model provider, is am I successful in terms of the ability to reuse these technologies and workflows? That's also something that you want to evaluate a project as successful or not. And this is more qualitative, but it's part of the success, and it's part of driving successful adoption of these technologies. Is, did it have impact on the users? Did you save them time so that they can engage on other high-level tasks that further drives optimization? And just another little comment on that. From the software development world, there's something called user stories, which are quite powerful little nuggets of information that you generate that can really just keep everybody on the same page of what we're trying to achieve, you know. And it's typically some person as some persona wants to do something so that he can unlock some kind of value, you know. So Bob, as a metallurgist, wants to receive notification for abnormal process operation with advisories for next action, so that he can focus on fixing the issue and spending time on optimization activities. And just having those user stories, and you can generate it during the business understanding phase, but having that little nuggets of what success looks like throughout this process really helps you keep focused on the task, and not just as if you're interested in machine learning, you're probably a little bit geeky, not just in making the nice code and the nice pictures. Okay, so the last part of the CRISP-DM methodologies on deployment, and the why it's a circular framework is, as soon as you've deployed a solution, you're generating new data, more value. The process is changing that you've now deployed in. So then you can start with the next problem, the next opportunity. But anyway, the interesting thing about machine learning, as I mentioned in the overview of this framework, is that they require care and maintenance. They require looking after, and that's something to plan for and to think about. What is that going to look like? How is that going to work? There's a really cool article by the team at Google called Hidden Technical Debt in Machine Learning Systems. And I didn't summarize all of it, but I really suggest have a look at it. And they show here a nice figure. See there, that little black block over there is your actual machine learning code, and all of these things around it, the size of it, kind of represent the amount of code that goes around just supporting, you know, your actual machine learning implementation. And there's lots of interesting things like, you know, data verification, collection, configuration, monitoring, all of these types of things that is really useful to at least have a sense of, or an understanding of. Not everybody has to be experts at everything, but as somebody that's interested in building machine learning models, it's worth it just to understand the broader context where a machine learning model that adds continuous value will live in, because that might help you in selecting your model and also selecting your data for your application. So have a look at this article. I think it really makes you think about models that will give lasting value. Then just a little bit of more of a kind of zoomed out a view on that. Like I said, the machine learning solutions do need a little bit of care and maintenance. So this is just kind of a view from my perspective, at least from a process monitoring perspective. I mean, the view is probably different for maybe some easier applications like machine vision, for soft sensors or something like that, but specifically for machine learning and process monitoring and data analytics and process monitoring, this is kind of my gut feel of where we are. So there's a lot of interesting challenges that prevent, automated models and analytics and apps completely taking over all process monitoring activities. And a lot of those challenges will be resolved in the next couple of years, but I think there will always be some persistent challenges. And I think we'll see a growth in automated analytics and apps, but I think the role of the human in the loop in some way will always remain, at least, well, in the next 5 to 10 years, because I think completely automated analytics decision support is not going, in a process monitoring context, is not completely achievable in the next 5 to 10 years. But I mean, there's a lot of potential of growth. But just a kind of a sense that I think the level of human involvement will be up and up the abstraction ladder with some support, just to make sure that when there's just-in-time data silos that need to be connected, or completely new events, or something that's more human-related, that's also covered. But the nice thing is, I think this automation kind of lifts itself up by its bootstrap. The more we have it, and the more we capture data around it. For example, these M&D and support services are logging cases and logging tickets and logging issues, which becomes a data source for text mining, which helps us improve the automated and analytics and apps, etc. I think there's definitely some multipliers that helps this journey forward. So yeah, that's just also something to take into account when you think about the deployment of your machine learning model. Can you leave it completely on its own? Probably not. So what is the implication in terms of the human in the loop support services for that? And what kind of tools can you develop to help those human in the loop support services? So yeah, that's the a reflection on using a bit of a more structured framework. I know it sounds like a lot of plumbing. There's the meat, there's the machine learning, but I've found that careful consideration of the plumbing can really make sure that the machine learning that you do is valuable. Yeah, so that's in a nutshell. We talked a little bit about some basic definitions and theory of machine learning, talked a little bit about the machine learning applications in mineral processing, a survey that we did a couple of years ago, and then just some of my reflections on how to do this with the CRISP-DM framework. I really appreciate you guys listening to me, and I'm looking forward to hear from Minx if there's any questions. We'll see how much we can tackle now, but I think Minx said that the ones that we don't get to, she'll send me a list of, and I can have we can try and answer them offline. Thanks.
Thank you very much, Dr. Oret. I appreciate you making yourself available for this presentation, for this webinar tonight. I encourage all our attendees to ask questions in the questions panel. We've got a first question from Lindelani Matumba asking, can regression be done with a Kalman filter for process data?
Hey, Lindelani, thanks for joining the webinar tonight. Nice to hear from you. So, can regression be done with a Kalman filter for process data? Well, my understanding, and I'm not an expert on Kalman filters, but my understanding is a Kalman filter takes the you've got it's a little bit like a hybrid model, because you've got a model of the data, and then you've got your actual observations of the data, and you combine them and take the best of both. So the model might be a database model, like a autoregressive, an ARX model or something like that, and then the data coming in and that combination. So can regression be used for a Kalman filter? Well, it feels like regression's already embedded in it. So that's my musings on it. I don't think I answer your question, but I think I just show that I'm not an expert on Kalman filters.
Thank you, Dr. Red. We've got a question from Ina Oosthuis, and it's something that I can answer. She says, hi, great session. Will the slides be made available? The slides are available, the presentation slides are available on request. You can send me an email. It's minx@saiee.org.za or webinar@saiee.org.za. And I will forward your mail to Dr. Oret, and she can then answer and use her own discretion to send you her PDF slides. Another comment from from Kimberly Casper. This was a nice lecture and very clearly explained. Thank you for your time. And then from Mehmood Hafaji, he says, no question, just a thank you for an amazing presentation. Dr. Oret is really comfortable on this complex subject matter and was absolutely brilliant. And I can agree with him. We've got another comment.
Much,
yeah, your presentation was brilliant, and I don't have any questions. I just got accolades for you from Kunrad Pretorius saying, thanks for the presentation. He says he's at least got a question. What are the practical applications of RL in mining?
So reinforcement learning in mining, something I haven't dabbled in myself, but I know that there's lots of interesting and exciting things being done around it. I think one of the reinforcement learning applications that's looked at is in a control system context, because controllers are already tasked with taking actions. It's kind of an easier framework to parachute in reinforcement learning. So I think one of the applications can be to see how they work with controllers, because you're able to take these actions. Something interesting for reinforcement learning for me, I think, just to be careful of, or what will probably be an interesting hurdle to overcome before a widespread adoption, is the fact that it's got agency. So how much do you want to trust an algorithm that's still learning to unleash it into your operations so that it can learn the best? So there's probably kind of a stairway to value, a stairway to training there, where you first unleash it on some simulations and see where it fails and how it's bad before you trust it, maybe on pilot scale operations if you've got. I remember my colleague John McCoy did an interesting survey on reinforcement learning in mineral processing a couple of years back. And I think one of the benefits perhaps with reinforcement learning is to, if you don't necessarily give it agency, but you do it as much as you can on a historical data set, that can help you learn some of the the structure that's in your data that you can use for other purposes. But I think I know Kevin Brooks is interested in it and looking at it, and I think Mintech is also researching it and looking at it. And I remember Chris Aldrich from Curtin University, I remember the paper probably 10 years ago now, exploring the concepts. So I haven't played with it myself. Look more at the unsupervised, supervised part of things. But I think those are the things top of mind that come to me. Yeah, I think that's what I can say.
Thank you, Dr. Rick. We've got another two questions in one from Kim Martin. Can you say any more on using process-based and statistical models together? Would you use statistical models to see if the PBM can be improved with the existing inputs, or alternatively, if key inputs are being excluded?
So this hybrid modeling concept is really interesting and really cool, and I think that review article, you should have a look at it. It's really interesting, and I think Prof. Ian Gregg's group at the University of Pretoria did an interesting paper on it. I think it was last year, or it might have been earlier, on looking at kind of hybrid modeling applications. But for me, some of the thinking that I've put into it, we've got a project on it at the moment, and we're quite keen to see where that goes. But for me, I see there's kind of a cross-pollination in a couple of directions, and one of the things is, if you've got a fundamental model, it's you had to make some assumptions when you set it up, and you have a certain set of inputs that you get out, and then you have your outputs, and you are now you do best as you can with your fundamental model. And then one of the hybrid approaches is to have your machine learning model in parallel. So it gets the same inputs as you had with your fundamental model, but it can make use of more inputs than your fundamental model, because of whatever is available in your process data. And then what it's trying to learn is your not the same output as the fundamental, but the residual, what your fundamental model predicted versus what the actual outputs were. And this is your residuals, and you're trying to see, you're basically seeing if there's anything left, if there's any information structure left. And then your machine learning model learns that, and then whatever structure it learns, it adds that to the prediction of the fundamental model. So they work together in conjunction. Now, one of the opportunities I see is that once, if this hybrid combination is successful, and you can actually improve your fundamental models by interrogating your machine learning models to see, okay, what is it? What additional information and structure were there in my residuals that wasn't captured by my fundamental model? So you could do variable importance on the input variables that you used for your machine learning model, and you can do partial dependence or these techniques that help you show how those variables in your machine learning model interacted to produce the information that allowed better performance. And by interrogating that, you can see what was it that my fundamental model maybe missed? Maybe there's new correlations between some of the input variables that you as a domain specialist, as somebody that understands the fundamentals, can see, okay, that's interesting. These input variables are used like this. This reminds me of this attribute. I'll use my enthalpy example again. So let's go back to my fundamental model and improve the model by looking at that aspect to include it into that model. So I can talk about this a lot, lots of thoughts about it, but I think von Stosch, who wrote the review article, has probably got more theoretical supported thoughts, so have a look at that. But this is one of the ideas that I think that this hybrid framework can lead to not just better predictions, but better understanding, to help you understand your process even better. Thanks for the question, Kim.
Thank you, Dr. Red. Excuse me. We've got another question here from Monsef Shao.
Hey, Monsef.
He's asking, did you experience a lack of labeled data in the industrial project in the mining sector? In the affirmative, how did you practically deal with this limitation? And then he went on to add, and great seminar, by the way, thank you.
Thanks, Monsef. Thanks for listening. I suppose it's a good time of day for you. So labeling, yes. So I must say, one of the coolest things for me when I joined Stand 3 and in this history was to see how they solved the labeling problem for machine vision, and I thought it was just such a good idea. So they crowdsourced their labeling. So they created a nice tool where they posted pictures of rocks, and they pay people a couple of cents per rock that you label. So fun way to earn some pocket money for for your upcoming holiday, is to get that kind of manual effort to label. And I think there's actually a lot of companies that now offer labeling as a service, because labels are so important. So that's quite interesting, and it's also luckily bootstrappy, because the more labels you've got, the more you can kind of improve your tool to maybe provide suggested labels, which makes the labeling effort quicker. So I thought that was brilliant. I thought that was really nifty. That's from the machine vision perspective. From the process monitoring perspective, no such luck. You can't give some time series data of a flotation circuit and ask, please, here's some cents, please label when there was a reagent pump failure, or where there was this kind of thing. So labeling for fault detection and diagnosis, big challenge. My experience so far is for that, there's that picture of Iserman that I showed. Those actions, what actions were actually taken to bring the process back. That's a real gap in mineral processing context, about where is that information kept, probably in maintenance logs, work management logs, SAP systems, and stuff like that. So there's definitely work to be done to more effectively, efficiently, completely capture that kind of data, and then to integrate that data sources with the time series data, with that kind of data. So no luck yet, but lots of ideas, and to deliver kind of a fault detection and process monitoring service. Our strategy at Stone 3 is to have constant communication and relationships with site, and actually we've got progress. We actually have progress, because what we've got an online case management system where we keep track of all of the advisories that we've give, and their history, and their observations, and the associated time series, and this becomes kind of our labeling. It takes a lot longer, but I mean, we're building up a very nice database of labeled examples in process monitoring. It's not quite the complete label as a machine vision context, but I think we're really that's going to be one of those multiplier effects that we'll see going into the future.
Thank you, Dr. Oret. We've got Kevin Brooks here that commented on your question from Kunrad Pretorius. That says Microsoft have something called Bonsai that does RL only on simulations, and so am I, he said. But we've got, that's it. That's all the questions we have for tonight. Dr. Oret, I thank you very much for joining us tonight and share with us your brilliant presentation. I thank all our attendees for attending this webinar. The recording of this webinar will be made available on SAIEE TV. And if you're looking for the presentation, please email me, as I've mentioned before, webinars@saie.org.za, and I will forward your mail to Dr. Oret. I thank you all for attending, and for all our ladies in attendance, happy Women's Day for Monday, and enjoy a great long weekend. And I thank you for joining us once again. Have a lovely evening. Good night.
Thanks, Minx. Good night.
Good night.
Het is soms al niet aan die